Welcome to this explainer. Today, we are looking at the absolutely catastrophic cost of taking shortcuts. You know, when you're building something massive, whether it's a towering physical skyscraper or a sprawling software architecture, skipping steps to save just a tiny bit of time or money can lead to some truly spectacular multi-million-dollar failures. We're going to explore a foundational programming concept that prevents these exact disasters, but first, I want to show you exactly what happens when structural integrity is compromised. And trust me, the stakes here are incredibly high.
Section 1. The cost of shortcuts. Let's start with a physical world analogy to clearly illustrate the sheer danger of taking structural shortcuts.
$350 million. That was the staggering original budget to build the San Francisco Millennium Tower. This wasn't just any building. It was a massive 58-story luxury skyscraper. And when you are building on that kind of immense scale, the physical foundation you lay down is absolutely everything. Software architecture is incredibly similar. If the base isn't solid, the whole thing is at risk.
But the developers made a critical, fateful choice. To save what amounted to just $4 million, which, let's be honest, is a tiny fraction of their total budget, they decided to anchor the building's massive frame a mere 80 feet deep. And worse, they anchored it directly into soft sand. At the time, sitting in a boardroom looking at a spreadsheet, it probably seemed like a brilliant shortcut to the team.
While the shortcut was anything but brilliant, the clay underneath the structure simply crushed under the immense, unsupported weight. This giant 58-story tower literally sank 18 inches into the ground. It tilted 3 feet over, causing windows to violently shatter under the sheer structural stress. Try to visualize that for a second. A brand new, ultra-expensive luxury skyscraper actively sinking and leaning over in the middle of a major bustling city.
And here is the ultimate irony of the entire situation. The developers didn't actually save that money. Not at all. They were forced into a total nightmare repair scenario. To stabilize the leaning tower, they had to spend well over $100 million to anchor it all the way down to bedrock anyway. A $4 million shortcut resulted in a $100 million structural disaster.
Section 2. The Knight Capital Disaster. Okay, let's dive into this, because we need to look at what happens when developers take those exact same structural shortcuts in digital architectures.
It results in this jaw-dropping figure, $440 million. Back in 2012, a massive Wall Street trading firm called Knight Capital experienced a digital structural failure of epic proportions. Because of a simple coding flaw, they lost $440 million in just 45 minutes. Just let that sink in. That is nearly $10 million evaporating every single minute.
This timeline brilliantly illustrates exactly how a software shortcut cascades into absolute ruin. Let's trace it back. 9 years earlier, the company created an experimental trading function called PowerPeg. When they stopped using it, they took a shortcut. They didn't properly delete or isolate the code. They simply left an old global flag sitting right there in memory. Fast forward years later. During a routine software update across 8 servers, engineers made a mistake and forgot to update the 8th server. That one tiny oversight accidentally flipped that old global flag back on. And in the 45 minutes that followed, hundreds of millions of dollars completely vanished.
Let's break down how terrifyingly fast this happened. Because their data wasn't safely encapsulated, the active system detected that active flag. It instantly ran the dead 9-year-old PowerPeg code. The zombie code woke up, and it went entirely rogue. It started automatically buying stocks at wildly high prices and selling them completely low, executing these disastrous trades millions of times per minute. Before anyone could figure out what was happening and pull the plug, the firm's capital was absolutely decimated.
Section 3. Procedural versus object-oriented. So what exactly is the technical villain of our story?
Now, what's really interesting about this slide is how it comes down to basic architectural paradigms. Knight Capital's legacy code relied heavily on procedural programming. As we know, in a procedural setup, variables and global flags are left totally exposed. They are out in the open, highly vulnerable to state changes from anywhere in the system. Object-oriented programming, on the other hand, fundamentally isolates that risk.
And that brings us to the hero of the story, encapsulation. We all understand the core idea here, bundling data and methods into objects and keeping those states strictly private, like locking them in a vault. But Knight Capital is the ultimate cautionary tale of what happens when we ignore encapsulation just to save a little time. If they had properly encapsulated their legacy trading protocols, a botched server update couldn't have possibly tripped a global flag. Encapsulation isn't just theory. It is the bedrock foundation that prevents a minor bug from spreading into a total systemic collapse.
Section 4. Scaling up software. Let's move to and see how this builds, especially when we think back to our own early days of coding.
Think back to when you were first learning the ropes. We were all building small, bite-sized programs, right? You were writing straightforward scripts for finding factorials, checking for prime numbers, maybe reversing a string. These were essentially little 20-line programs. And honestly, for something that small, you really don't need a massive, robust blueprint.
Back in those early days, your focus was entirely different. The only things that really mattered were pure computational efficiency, big O time complexity, meaning how fast your code ran, and space efficiency on your local machine. It was all about the pure math.
But that completely changes when you start scaling up. You are no longer just reversing a string in a terminal window, you are building real-world platforms. Think about massive e-commerce stores processing thousands of global orders a minute, ride-sharing apps constantly matching drivers and riders in real time, or sprawling university portals managing highly secure student data. The sheer scale and complexity are just on a completely different planet.
So the crucial point here is that when you reach this massive scale, raw computational efficiency actually has to take a back seat. To prevent a total systemic collapse, your priorities must fundamentally shift to these three pillars: maintainability, modularity, and structural stability. You can't just write fast code anymore. You have to write code that is logically organized, highly modular, and safely encapsulated, so one tiny error doesn't cause a sinking tower or a $440 million glitch.
Section 5. The Golden Engineering Rule. Let's look at the ultimate takeaway you can apply to your own work.
To wrap this all together, there is a piece of practical engineering wisdom that you can take directly back to your code base today. It's known as the 1 to 10 rule, and it is absolute gospel in software engineering. Let's read it together. Every 1 hour you spend mapping out your classes, data layouts, and system designs on paper saves you at least 10 hours of nightmare bug hunting, painful code rewrites, and system crashes down the road. Planning your encapsulation and designing your objects isn't a frustrating delay, it is literally the strongest possible foundation you can pour for your software.
So as we wrap up this explainer, I want you to look at your own code today and seriously ask yourself this question. Are your variables safely inside a locked box, or are you leaving them exposed for a $440 million disaster? Keep building, keep learning, and I will see you in the next explainer.